Hello again. In this video, we'll start out by looking at this example. Follow my cursor. The limit as x goes to 0 of 1 over quantity 3x plus 4 minus 1/4 is equal to limit x goes to 0. Now we need to get a common denominator. Remember, we do 4 times this one right here, and we get 4. And I do 3x plus 4 entity times 1, and I get entity 3x plus 4. But guys, we are subtracting. That 3x plus 4 is on the tail end of that minus sign, so we got to put parentheses around it, and those parentheses do matter. And then we put that over the common denominator of the 4 and the 3x plus 4, okay? Now, and all of that whole fraction is over x. Now remember, we don't care for nested fractions, right? So I bring that 4 and that 3x plus 4 down below. Now by commutativity, I can just put the 4 to the left, and I can put the x next, and then the entity 3x plus 4 last. I could write this in other ways, but they would look awkward. This isn't the nicest, prettiest way to write it. You know, you could say x times 4 times 3x plus 4, or several different, there's 6 different arrangements you could do, but, you know, I don't want to get silly about it. Okay, but lo and behold, the 4 and the minus 4 will cancel each other, leaving you a negative 3x over entity 4x times 3x plus 4. Okay, now that x is left by his lonesome self, and he's vulnerable. Aha. This x right here and this x right here are going to self-destruct. They're going to cancel by division, leaving you with just negative 3 here and just 4 and the 3x plus 4 here, without the x there this time. Okay, but guess what? The golden goose. We canceled the x's, and we can... That's going to allow us on this step right here to throw 0 in directly. Well, yeah, sure. I go ahead and do a trick first. I take out the negative 3/4 just to get it out of my hair. But I could have actually went ahead and threw in 0 here, but oh well. The next step, it skips a line, but I put the times sign here to indicate that. So I got negative 3/4 times, and then I just throw in the 0 into x here. I make good on my promise. But 3 times 0, by order of operations, I go in parentheses, I do the 3 times 0, that is 0, 0 plus 4 is 4, and then I got 4 times 4, which is going to be 16, so I'll just cut to the chase and go right here where my cursor is now. So that's one, I got negative 3/4 times 1 over 16, and that's negative 3 over 64, so there's that. And, but anyway, hope that helps. Now, I gave you this one down here for you to do. Big, huge hint. It should have some semblance to this one right here. There should be, you'll do it in a similar fashion. Now, instead of x that's going to be left vulnerable, there is a little bit of a slant difference. You'll have a parenthesis x minus 1, okay, that should be left vulnerable. And anyway, I'm going to sort of leave that one for you and see what you can do with it. You know what? I do need to be careful about something, though. No, let's not do that. Let me just let that one go, okay? You know what, guys? Let's not do that. I take it back. Let me just put a 0 here. I might create something more creative later, but sorry, I messed up. That's my bad. Don't do that. Do this, okay? And I'll save that in my changes. But yeah, just do this guy. My bad. That other guy would have actually been a bad guy to have done. Sorry about that. So this is what I intended, or this is what I intend you to do. So, and there'll be some similarity. Just use this one as a Modelo. I had something clever in mind, but it didn't work. My logic went sour, but this is good here. So just do this guy right here, okay? And I went ahead and saved it already, so the bad guy won't be there. When, you know, I'll give you this Word document to have later on. Anyway, okay, let f be a function from r to r such that f of x equals the cube root of x, which is x to the 1/3 power. That's what it means to be raised to the 1/3 power. Then f prime of 0, well, we get positive infinity if we try it. Guys, but we don't allow for the infinities when we do differentiability. That's That's not a good thing. We want a derivative that's finite. Hence, f is not differentiable at 0, 0 because we don't allow for infinity. Positive or negative infinity, for that matter. We don't want either type of infinity. Okay. Now, here's the thing, though. With the cube root, we get a slope, we get f prime equals positive infinity, but we don't allow for that to be classified as differentiable. The cube root, anywhere that's not 0, it is differentiable, but not at 0 itself. Notice, though, it did have a predictable direction. What that means is we will have a tangent line at 0. It'll be a vertical line. But the thing about a vertical line is, one vertical line, you could classify it as having a slope of positive infinity, but you may get another vertical line on another example that would have a slope of negative infinity, so we just leave the slope of a vertical line undefined. We don't go there. It's just a bad place to go. Okay, now let f be a function from the reals to the reals, where we get x to the 2/3, and we get that. Then f prime of 0, it doesn't exist in even the direction sense. You wind up with, you do the limit of, the cube root of f of 0 plus delta x minus the cube root of 0, which is just 0, which doesn't amount to anything, so I left it off, over delta x. And guys, that's going to be the cube root of delta x squared. That's going to be, that's delta x to the 2/3 power is what that is. And you'll do 1 minus 2/3, which will leave you a 1/3 down here. That's what's going to happen. And you'll be left, I kind of do it a little bit differently. So I just write it as exteriors here and here. And it's going to give you the same thing. But the limit as x goes to 0, 1 over the cube root of x, that goes to positive infinity from one side, namely the right side, negative infinity from the left side, so it doesn't even exist in the direction sense because of this right here, like I was talking about just a second ago, and this right here. So it's not differentiable at 0, 0 in a different kind of way, but in any event, neither one are differentiable at the origin. It can be proven that if a function is differentiable at a point, it'll be continuous there. Aha! Notice something, just like the absolute, sort of like for the absolute value, well, yes and no. Notice, though, the cube root function, if you ever graph it some way, you'll notice that there's no sharp place or any kind of kink at 0, 0. You're smooth. It's just that your tangent is infinitely steep. That's the only problem, but that's enough to run things for differentiability, okay? So for the cube root function, there's no sharp point, there's no cusp or anything like that, and it's just, the tangent's infinitely steep. You're infinitely vertical at that one point. If you were to, the break-off tangent line is vertical at the origin. That's the trouble. Now here you get what's called a cusp, and follow my cursor. You get this, you'll go down like that, and then you'll turn around and you'll kink back up like a crooked V and go up like that. The alphabet letter V, well, that kind of looks like absolute value, but imagine that but it's not, imagine a letter, it's not absolute value though. Imagine the alphabet letter V, as in Veronica, but it gets infinitely steep here. So the slope, it may be going to, let's say, negative infinity here, but then you kink back up, and the slope would be positive infinity in this way. So it's like a letter V, a crooked letter V. That's what the graph of x to the 2/3 looks like. It doesn't look anything like x to the 1/3, not much at all. Now the V would actually go up forever, though. It's like a crooked letter V that goes up slowly in both directions. But here at the sharp kink, it's infinitely steep coming in from either side. That's called a cusp, C-U-S-P. So you'd do this, and then you'd stop, and then you'd kink up symmetrically like this. It'd be symmetric on both sides. But anyway, this is an even function. This is an odd function from algebra. Odd means that you get the same graph if you reflect x to the 1/3 over the x-axis and then reflect what you get there over the y-axis, you get the same graph. That's an odd function. X to the 2/3 is an even function, which means if you just reflect it about the y-axis, that you'd get the same graph again. And when I said same function, I meant same graph up here. So if you took the graph of x to the 1/3, flip it about the y-axis, then flip it about the x-axis, the order doesn't matter, then you would get the same graph again. That's odd, or origin symmetry as they call it, okay? But anyway, there's that. So differentiability implies continuity, but the converse is false. Again, now guys, we were actually in both of these functions here, and for the absolute value function, they all three have they're all three a little different at the origin, but they have a commonality about them. They are continuous at the origin, yes, but they're not differentiable at the origin. The absolute value is not. This x to the 1/3 and x to the 2/3, they're not either, neither one of them. So they're all three continuous at the origin though, but just not differentiable there. Absolute value of x has a kink. You know, slope is -1 coming in from one way, +1 coming in from the other way. X to the 2/3 is a cusp. The slope is positive infinity coming in one way, negative infinity coming in the other way. That's a cusp. And then this guy right here just is actually totally smooth. It's not sharp at all for x to the 1/3. It has an infinitely steep tangent. And the derivative goes to infinity in a predictable way, but that's not going to save our derivative. So that's that for that, guys. And so I just wanted to go over that. So jagged, when you see a jagged points, if a point's jagged, we've probably lost differentiability there. And I really ought to be concise, and let's just say jagged points. So jagged points are a good indicator that differentiability does not hold at that particular point. So there's that. And again, the cube root is more interesting. It is smooth, but it has a derivative of positive infinity, quote unquote, there. But again, we can't have that. And notice I put that in quotes. But differentiability demands that the difference quotient limits be finite, so we can't classify it as the cube root as differentiable there, even though there is a certain type of quote unquote smoothness there. And all of them are continuous at the origin. And now let's move on to the next video. This will take a little bit of time. Thank you guys. I'll see you on the next video.